question can I possibly One thing will be that there is a step ratio in the transformer. So if you want to go from a lower voltage to a higher voltage, then we're going to be increasing the voltage in this direction. But if you go from the higher voltage to lower voltage, then you decrease the voltage in the transformer. But the transformer is not the only thing that determines the output voltage, because there's also duty cycle in here that also has an effect on that. So the problem that was in the book on the quiz was from 12 volts go to 24 volts, right? So it was an increasing step-up rate. If we go the other way, we decrease. So which one would you like to look at? The increasing or the decreasing?
Increasing.
Increasing? Okay. So we'll do the increasing. You do.
Which one's more complex? Like it's basically the same thing, just different step ratios, right?
Yeah. There's no difference in the analysis. Same. All right. So if we want to do the increasing direction, then let's say we want to generate a voltage here that would be equivalent to 8 lead-acid batteries. So it's 98 volts. But it's a standard voltage for half of the DC motors probably used for traction. So 98 volts is supposed to be here. That's our design criteria if we want to design it, right? We want 98 volts at the output. So that's one thing. And we would want to have a certain amount of ripple in this current, right? Because we want to use this inductor to limit the ripple, but we don't want to have this inductor too big, so we have to allow for a certain ripple in here. Now, what kind of level of power would we want to get? Let's say 5 kilowatts. Well, there's only one transistor, so maybe let's scale it down to 1,000. So that's the output power. And this way we can figure out what the current should be when it's loaded. This is a forward converter. Can you disconnect the load and turn it on? For the forward converter, you can. For the flyback, you shouldn't. It's not the best. Yeah. Maybe. So the level of current here would be based on that power. Voltage times current is power, so power divided by voltage is current, so that's 10.2 amps in here. So that's I0 and 10.2 amps. And that's going to be pretty much a constant current because we assume that we have good enough capacity there, so whatever ripple of current we have is further going to be filtered down by its capacity. So we can pretty much assume that's a constant voltage because of the capacity. And that's going to be the average current through this inductor. Inductor will have the ripple. And whenever this voltage is positive like this, the current of the inductor is also the current through this transformer. But when the voltage turns negative because we turn off the MOSFET, and this current switches over to this diode, and you're going to have no current through this secondary part. But now that we know that there is going to be some ripple in this inductor, let's graph the current through here. That's IL of this inductor. let's say we have a duty cycle in it, and the duty cycle would be 40%. Good idea to use 40% because you can go up to 50%, because once you build it, you're going to put some extra losses and you will not see 1000 watts, it's going to be only 900. It's not good with this voltage, right? It's never reaching your level, so you have a buffer zone on the duty cycle. You can increase it from 40 to 50%, hoping that then you can get to 1000 watts. So we have 10 amps over here. That will be I0. And then the current is increasing here, and then 60% of the cycle is going to be decreasing. And then 40% of the cycle is increasing, and then it's decreasing. And the question would be, what kind of ripple do we want to have so we can calculate the value of inductance? Let's say 10% ripple in the output current, and 5%. Let's say we want 5%. And this is 5% from here to here. It will be 5% times I0, so that is the ripple of this IL, and I'll call this delta IL. So now the current through here, the secondary current, maybe let's call it IS. It will be same as this current over here, and then 0 through here, and then this and 0. And so that is the current. So we'll get to calculations of the ripple in a minute. Let's first look at what we have for the other two currents. These two will be the current IP, the primary current, and then the current of recovery. I'll call this IR. Recovery from magnetization. Right? The difference of these two will be I1. Now, there's going to be a step-up ratio in here, 1 to K. And we want to generate 98 volts, maybe from 48 volts or 24 volts, maybe 24 volts. So this is 24 volts in here. On the test, we're going to ignore the voltage drop here and the voltage drops in here. That's going to make it a little bit simpler in our equations. In the problem we had 0.7 volts and 1.1 volt in here, and that mainly affected the efficiency calculation. Right? But the efficiency calculations were bogus anyways, because we completely ignored the switching losses. So yeah, if you run it at the very, very low frequencies, that would be justified. But you would have to include the switching losses if you're really serious about those calculations. So we're going to ignore those voltage drops. What we have in here in this current, IP, we're going to see the copy of IS for sure. That's going to be one part of that current. So we're going to see something like this on IP. Now, since we're splitting the voltage up, we're going to have much stronger current on the input than on the output side. That's why I use a different scale so I can use the same shape, but it's going to be, scaled down. I just copied the picture of this. That doesn't mean that they are equal in the value. We're going to have this in IP. And in addition to this, since we're applying a voltage here across this inductor, 24 volts, there's going to be also magnetization current on top of this current to kind of add up together. So I'm going to add that other current on top of it, just to show that all is going to be there. So I have a copy of that current, and on top of that, this is going to be the actual current that flows through IP, or that IP current.
What is that part you're on? I was copying.
Hmm?
What did you just draw?
This one here is simply IS
Okay. And then that's
times
plus.
K. K times IS. And this is the actual IP. Because in addition to that current, we also are going to have magnetization because there is inductance here, L1. And there is an equation that voltage V1 will be L1 times some delta IP divided by the duty cycle. Well, we were using K for duty cycle, right?
Okay.
So I'll change the K to an N here. From this to N. And that's going to be N. And this one here is operated with a duty cycle of K, which is 40%, let's say. So if this is the period T, that is K times T.
It was supposed to be IS plus N, which is. No, I was saying, do it supposed to be IS plus N or just.
Times N.
Oh, okay.
IS times N. N times IS.
Alright.
And the difference, which is here, is the small delta IP, which I am now writing an equation for, and this will be K times T. That's the change in time. So the overall ripple of the current IP, and that's again, it's not a very good term, ripple, because the ripple would have to include all of this, right? But if you want to say how much it changes, it's not really a ripple, right? It's just how much it changes in here. It's going to be a 5% here plus some extra from magnetization. Let's not worry about calculating this yet. Let's get all the waveforms on the picture first. Now, when you turn off the MOSFET, the secondary current disappears to 0. So all of this part is going to disappear completely to 0, but this piece is going to remain, and that piece flows through that recovery transformer winding to be returned back to the voltage source. And since it increased due to the same voltage, because we're returning to the 24 volts with the same level of inductance, let's say same level of inductance, it is going to take us about 40% of the duty cycle to come back from this value. So I'm going to make it like this. And this current can have a good, it says squiggly line. This is the recovery current. Nothing here. And goes up to this level. And this one here is IR. I don't know if that's any more clear or not, where it's coming from. The essential part is that we have two slopes to consider here, and this slope wouldn't be even considered if this was infinite inductance. Then that value here would be completely flat. But since it's not, it ripples a little bit, so we see that. And in addition to this, magnetization of the transformer is an extra increase. Question?
What does that line above the inductor mean? Does that just mean it's coupled with something?
No, it's just fancy. It's a fancy symbol for a choke, because the chokes are big and they have a core against the core, right?
Oh, I see.
Yeah.
So the, before we had the magnetization current sloping up, so that's not a 5% ripple like on the other side, because we're stepping up the current to that side, right? So it'd be 5% times N
Well,
before we had the magnetization current.
before we had the magnetization current, this slope in here is same as this slope in here. It is 5% of that value. This is 5% of that value. Well, this is 5% of this value, right? Well, that's nothing. That's not the average value of the input current. We can refer this to the average value of this current overall if we wanted to. But then that's not going to be then 5%, it's going to be some other number. We can calculate numerically the value because the delta of IL times N is going to be the delta of this current IS times N. I don't know what to call it. But the value from here to here, let me write this down.
That little triangular section.
Yeah, the value from
That's what I was asking.
here to here, right, will be delta IL times N.
Okay, yeah, that's what it was found. Thank you.
So we have all the currents now. Now the voltages. There is voltage V1 that is applied to that transformer in here. Second, you turn on the MOSFET. Once you turn on the MOSFET, N times V1 shows up in here. If you had a loss, or if you had a voltage drop on the transistor, then over here you get N times V1 minus some V2 drop, right? But we ignore that, so we just have N times V1. And then if you ignore this drop, that voltage shows up in here. So the voltage at this point over here, I'll call this some point, no, this is point X. I'll call this a point Y. It becomes that value times N, so it's a higher value here. And then it drops down to 0 because there is no voltage drop here if it's an ideal diode. When we turn off this MOSFET, this inductor keeps this current moving, and it opens this diode, so that makes that voltage drop down to 0. And then it reappears over here, and then back to 0. And then come up. And this point is N times V1. So this is the voltage Vy. We can also talk about the voltage
So
Are they supposed to be the same height?
over here.
I think so. Cool.
Are all those voltages supposed to be the same height?
Yeah.
Okay. That's all right. I just want to make sure I wasn't criticizing.
Yeah, it's when they're standing here, they look equal
Big.
because pointing down. I was listening to a program on the radio where they were discussing this painter, Vermeer, that was painting some pictures. And they figured that on his pictures, which he painted, all of the colors that you have on the painting are nearly perfectly representing what was being painted. And they know now, scientifically prove this, that the human brain is incapable of remembering color. So by looking here, you cannot replicate the same color. You have to have them looking at them at the same time and comparing them side by side, looking at the same time. Then you can replicate the color. So basically they figured what kind of device he had to have to paint those pictures. And it wasn't a camera obscura because that does not reflect the color of the shades. So he figured out some other contraption to be able to look at the reflection of what he sees and his canvas so that he can adjust the color of the paint. Alright, so that was that voltage. Let's also put the voltage of point Z over here, which is same as Y when this diode is open. So that will be that. But now, when you turn off the MOSFET, so this current doesn't flow, so that this voltage over in here is not generated from that winding, because that winding is now passive. So nothing is putting out a voltage for this inductor to conduct, so the inductor opens that diode because it has inertia of the current. So this voltage becomes a zero, so that voltage for sure is not going to be positive. It has to be at most zero. It could be negative, right? Because it has to be, because that diode, if this voltage is negative, will be open and not conductive. And then what happens when you disconnect this winding and this winding is disconnected, there is inertia of IP because of this. We magnetize the core, and that core wants to have some current going through, and that's going to be this current. So what we see now, this current flowing like that is going to put 24 volts at this point and 0 volts at that point. So we're going to have 24 volts positive at the dot, which makes it n times 24 volts positive at this dot, so this point is negative n times V1, n times 24 volts. So that's going to be an equal value, just negative, for this second voltage. So I'll make it like this. So that's the voltage VZ. That's not exactly true because if you look at this, it looks like this voltage here is not exactly with the average value of 0. When you have an inductor and there is a steady state, there is a current that has an average value. So the current is not constantly increasing to infinity. If on average the value of current stays at the finite value, like those, there is an average that doesn't change, that means that the average value of this voltage has to be equal to 0.
So it's offset.
So what's happening? This is not exactly lasting all that long, because the second this one stops conducting, because it eventually is going to discharge the cord, this one will stop conducting, that diode, at some point where the current decreases down to 0. When it decreases down to 0, there is no reason to see any more of that voltage there. That voltage is going to become 0. Because now all of the windings are passive, none of them is conducting anything. They're just waiting for the next cycle to start. So that would be the voltage at point Y and Z.
Are those lines just drawn different, just to differentiate the signal?
It's different colors.
Okay, okay. I wasn't sure it was the
Yeah, so the output voltage is, I suppose, this one. I'm going to mess them up.
And it's NV1 and negative NV1, right?
And this is the negative NV1, yeah. So this one here is the V sub Z. And the bold one is V sub Y. We should also probably show the voltage Vx, but we cannot use the same scale. To show what's happening with the boiling point of Vx. Obviously, when you turn it on, that's 0. But as you turn it off, you get 24 volts in here. And that one is showing 24 volts in here, which gets transferred over here, so we have twice V1 in here. It's 2 times 24 volts. For as long as this diode conducts. Because when it stops, this voltage drops down to just 24 volts. So what we see there is, I want to add to this graph, so I'm going to just graph it over here, that's the point of Vx. So for the first cycle, say it's 0, then it goes to twice V1, and then it drops down to only V1, until the next cycle starts. So it resembles the shape of that, it's just shifted up to the level of 0. And if you look at the voltage at any one inductor in here, between this point and that point, sorry, that's centered around G1. The average values are 0. And that Vy, which is this one, is not across the transformer, so that doesn't have to comply with that rule. Only the Vz has to have an average of 0. Yes?
When VX does your little stair step there, that's kind of that 40%, then the last 20%, then it goes down, right?
Yeah.
Okay.
So this is KT. And that's T. And this, if these two inductors are equal, this is one KT, this is another KT. So what's left is that 20% right here. Now, this way, we have every picture to start completing the calculations. If you want to have in here 98 volts, And this is just a low-pass filter, right? If you look from here to here, it is just a low-pass filter, so that the average value of this voltage is the average value of that voltage. So the average value of the voltage Vy has to be 98 volts. And we have a duty cycle involved. We're looking at the bold line here, where this point is the KT. We can figure out what this maximum voltage should be to give us the average voltage of 98 volts, which is about here. This is the V out. The equation for V out is, duty cycle K times N times V1. So without those losses, that's a very simple equation. You have the step ratio of the transformer times K. And N times V1 first will be 98 divided by the duty cycle of 0.4. So that's 245 volts for this one. 245 volts. So we have now this value calculated. We can figure out what the step ratio should be. It is 245 divided by 24 volts,
10.
and we have 10.2. So the K, or this N, should be 10.2. So I didn't put those numbers into here. V out is 0.4 times 10.2 times 24 volts. Let me see that works. 0.4 times 10.2 times 24, it's 98 volts, yeah. Now we can go back to this inductor to figure out the business of the ripple, because now, yeah, I can just do 45 volts again. Well, 24 volts was that initial statement that we wanted to use 24 volts as an input source to make 98 volts at the end. Okay. And then we have this equation here that duty cycle times the step ratio of the transformer times the input voltage is the output voltage. So now we have two phases of increase, either this one or that one, or this one and that one. If we just want to do an increase, then we have here 245 volts, and we have here 98 volts. That difference is driving this increase. We can calculate the inductance value. Or we can look at the sloping edge in here, where all we have is just the 98 volts, and slope of that line is determined by this inductance, and we know what the average value is, so we didn't really have to know this voltage of 245. We could have already calculated what that inductance is. So maybe let's do it that way. Looking at this slope here, that is that value L gives you the voltage of V out over here. So we have the V out is L delta IL divided by the change of time, which is 1 minus K times T. So from here I can design the inductance value, which is 0.6 times what's the switching frequency. Let's use 10 kilohertz. Times the voltage V out, which is 98 volts, and that's divided by delta L, which is 5% of the loading current, which is 10.2 amps. We're just very unfortunate that this number numerically is exactly the same as that number. It just happened accidentally. Okay, 0.6 times. Oh, that's 10 kilohertz inverse, right? So for the frequency of 10 kilohertz, the period is 100 microseconds. And that's what should go in here. So 0.6 times 100 times 98 divided by 5% of 10.2 amps. I have 11.5 of a millihenry for that output impedance. So we got that part done. The only one thing left in here to design would be to figure out what the value of inductance L1 should be to accomplish that kind of a ripple. Normally what you care about the most is how far you magnetize the transformer. That would be your design criteria. So the criterion would be the slope here overall, but especially this one, as the magnetization of the transformer should be this is the transformer. The magnetic flux density, which is the B, is here. It's in Teslas, right? Well, you don't go all the way up to the saturation, but you don't want to over-design, so you would be probably somewhere here with the maximum, right? So this would be your maximum B. So on top of that global curve, we're going to have the actual curve that you're going to transfer on. So this is the primary magnetization curve. So that curve is going to look somewhat like this. It's going to be kind of in parallel to the big one, but it's going to be slightly smaller. And if you integrate this curve in this coordinate system where you have the H and the B, you want to find the surface area included inside of that inner one. That's your loss every time you switch, right? That's going to come out in terms of work every time. It's going to be joules. And you switch at that frequency, so you multiply this by the frequency, and you know how much power dissipation you're going to have in the core with that kind of magnetization. Now this curve is not best looking. Let me try again. This is primary magnetization, this S-looking thing. They're going to operate somewhere like this. And if you overdo it, you're going to go all the way up here. The curve is going to cost you much more loss. This is going to look like this. So just not going all the way up to the saturation level, just keeping it at 80%, you greatly reduce how much loss you have in the core, right? Because that curve encloses much bigger surface area than this one.
Now, why did you plot B against H? Isn't B just a scalar multiple of H? Or not scalar multiple, but a,
That's how we teach electromagnetics. We always say that V is equal to mu.
yeah.
So that's the key in open space.
Oh, okay.
In the open core, that no longer, I mean, in the magnetic material, paramagnetic, that no longer calls.
Right, you
It's
have,
not even a curve. It's not a function. It goes this way differently than that way.
right.
So
That's
that
not
is,
1, 1, so it can't be a function. Or not 1, 1. I mean, it doesn't pass the horizontal line test. No, vertical line
no,
test.
it has history. That's the biggest
Or,
part.
yeah, histories is, yeah.
So in order to have this actually written up, you have to have 5 variables. So with the 5 variables, you can actually write this as a state equation. That is going to have the H and the B as 2 variables, and there's going to be 3 other variables inside that are kind of hidden. That gives you access to why is that like this. And SPICE actually has that model inside.
Oh, really?
You can run the hysteretic curve. That will allow you to calculate those losses. By the way, it's time to turn it on, right?
Oh, yeah, I guess so.
I'll just go back to the voltages and see what happens, right?
It's like when they talk about dielectric losses due to complex permittivity, right? Only it's permeability.
Yeah, that's pretty much the same thing. You have to rotate. What was supposed to be the
Minus
duty cycle?
58%, right? So, what, 58%?
It was 116 at some point.
Yeah.
It will keep dropping now because it's warming up.
Have you tried or what kind of frequency do you increase it to?
It's 400 hertz now.
You're not be able to keep up, just because it's speeding up so much now, especially as they increase the frequency. I think I found like for mine, it had to be somewhere around 600 hertz or something.
Oh, that was a mistake. Now I cannot turn it back on because it's going to blow.
Wait, what?
It will blow up because it has no average current going through, and you have to charge up the output capacitor that causes the surge. And if you're at the verge of what it can do, if you kick it with this current, most likely that's what it fails. So if you have a microcontroller that drives this, you always step it up, gradually. You never turn it on full power. All right, so we're going to ignore those losses in here. I don't know even why I'm talking about this. Oh. This is the B. And we wanted to talk about how much we actually put into that core every time. That would be this magnetization. But this is really a secondary effect that is unwanted for us. That was essential for the flyback because that's where we keep the energy to then throw it to the secondary side. So we actually do want to use up as much as we can without too much loss, because that power, that energy would be then transferred in the flyback to the secondary. This one doesn't use it at all. What happens is that it raises the voltage, and this current tries to magnetize, but that one is demagnetizing at the same time. They are subtracting from each other. So we get that power transfer for free, but it's just, as a secondary effect, it gets magnetized because we keep the voltage across for a while, and that's what it is. And this equation for B is the intensity, flux density inside of the core. Density means that if you multiply this by A, you get the magnetic field just the flux, actual flux, not flux density. And the derivative of that with respect to time is your voltage, V1. So you don't need to know what the inductance is. Once you have that curve, you have all the information you need to see how far you're going to magnetize it for that core. And then we would have to be talking about some cores now to be able to answer that question. But if
What's
you don't
what's A?
Oh, the surface area of the core.
Okay.
If you take that transformer and cut it, you're
Mhm.
going to see the surface area of the metal inside. That's going to be the A.
And that's just on one side of it. If it's a square, right? It's just
The middle
Yeah.
one, because there's three of them.
okay. Thanks. I don't think anybody's ever specified.
Or you can add the two sides. Right?
Okay.
That's the same thing, because that magnetic flux is going like this.
Is the two sides additive or just one side?
They add. So they even are designed this way that if you take the surface cross-sectional area, you're going to have this, and then you're going to have half of that on one side, and the other half on this side.
Okay. And that's like an E-style core?
It's an E-core, yeah.
Okay. Thanks.
And then you have the windings going around in here, so you have some kind of a bobbin going around. All of the wires go through here. Well, that's what you see.
And you add all three of those surface areas together.
Yeah.
Okay.
So that's the E-core. So that's A. No, this is A.
Oh.
Or this plus that.
Okay. Thanks.
Because then you have the other half going up this way, right? And it closes up the